Hello and welcome back. In this video and a few others to follow, we will be talking about communication protocols, and we are going to start with the UART, which also stands for Universal Asynchronous Receiver and Transmitter. And this video is going to be the theory just to help you understand a bit about what a protocol is and how the hardware interface looks like. And then in the following videos, we will start writing code to send and receive information via UART in different ways. And then we will also go to the oscilloscope to actually examine how data is actually transmitted using the protocol. So like I mentioned, our focus is going to be on UART. Why is this pen not writing? Yes, this is a pen. Okay. And then UART. Yes. So UART. And like I said, it stands for Universal Asynchronous Receiver and Transmitter. Sometimes it is also called USAT, which is just Universal Synchronous Asynchronous Receiver Transmitter. It's the same hardware interface, but it can work in synchronous and asynchronous mode. So don't get confused when you see UART or USAT and it's using the same hardware. Before I explain the details of the UART protocol, what is a protocol? This is what I want us to take a look at. So what is a protocol, right? And a protocol basically is a set of rules that governs communication, basically. So for example, English as a language, or any other language for that matter, has some rules, right? Which is known as the syntax and sometimes also the semantics of the language. So for example, in English, I cannot say she didn't came, right? It is part of the rules, it is part of the protocols of the English language. There is a rule such as subject verb agreement in English, and I believe in every other language. When it comes to hardware communication, there is also the need for a protocol. This states the order and the manner in which the two hardwares or any number of hardwares using that particular protocol should be able to exchange information. And so UART or USAT is just a hardware protocol. And in UART, it is a peer-to-peer, okay? So I'm going to write P2P. Unlike other communication protocols where there is a master and a slave, in UART, there is no such thing. It is peer-to-peer, okay? And I'm going to draw the hardware interface very soon. But UART basically helps you to communicate between an MCU and an MCU, or an MCU and a sensor, or an MCU and your PC. But for this, you need what is known as a UART to USB converter, which we will talk about very soon. So now let's talk about the hardware interface. If let's say this microcontroller here, and I'm struggling to draw with the mouse here, but it still gets the job done. So let's say this is an MCU, and this can be an MCU, it can be a sensor, or it can be another computer with a USART USB converter. What is going to happen is that each of the participants have what is known as the transfer pin, or the TX, and then they also have the RX pin, and then this is also going to have a TX pin, and this is also going to have an RX pin. And of course, for them to communicate, they will have to share a common ground. Okay. Now, let's say this microcontroller wants to send information to whatever this one is. Let's call this A. So I'm going to call this A, and then I'm going to call this system B. So let's say system A wants to send information to system B. You need to connect them across. And what I mean is that the transfer, so this one is going to transfer, and the transfer pin of system A has to go to the receive pin of system B. In the same way, if system B wants to send information to system A, you have to do the crossing. So it will transfer in this direction, and system A is going to receive in this direction. The mode in which this works could be full duplex, which means you can be sending and receiving at the same time, or you can only be sending or receiving. It all depends on how you configure, but the hardware interface has support for these different modes of communication. Now, one thing that is very important is, because they will be communicating, there is a need for a protocol such as I have described already. The protocol dictates how do you signify that you want to send me information, right? And then how do you signify that you have finished sending the information? These two are very key. So there is the start condition, which we will see when we look at it on the oscilloscope. There is the stop condition. There is the number of bits that will be transferred. And very importantly, there is what is known as the baud rate. So this is the speed at which the communication is going to happen. So if microcontroller A or system A wants to send information to system B, they have to, first of all, agree on at least the number of bits that will be transferred, so that if system A says I'm sending 8 bits, then system B knows for it to receive a full word, it has to read 8 bits. Also, there is the baud rate. Common values for baud rate are 9,600, and then there's 115,200. But there are a lot more baud rates that you can configure, but these are the commonest ones that I have seen. So the moment system A indicates to system B using the start condition that I want to send information, system B is going to begin to clock at the baud rate, the agreed baud rate. That is the speed of communication between them. And it's going to sample the line. So this is system A sending information to system B. So system A is going to indicate or signify the start condition. Usually the start condition is, once you set them up to communicate, the transfer pin is held at high voltage level. So if it's a 3V3 or 5 volt logic, it's going to be held at 5 volt or 3V3. The moment system A wants to send information, it's going to take the transfer line down to logic level 0 for 1 clock cycle. And that is what is going to signify to system B that, okay, system A is ready to send some information. So on system B side is going to start sampling the line on depending on the baud rate and also the number of bits that they have agreed to transfer or use to communicate. That's the protocol, right? So it's going to sample, let's say it is configured to transmit 8 bits, which is common. You can also do 7 bits. Then it's going to sample this line 8 bits or 8 times at this baud rate. And after that, the system A is going to indicate a stop bit. And the stop bit is basically taking the line back to the usual state, which is the high voltage. Apart from all these that I have written here, there is also what is known as parity check. These are all configurable. Now, parity check is, let's say, a safety mechanism that is included in the UART protocol so that system A can tell system B the oddness or the evenness of the data that it sent. That way, when system B receives it, it can check to confirm that the communication has not been corrupted, like the transfer of information has not been corrupted. And these are all configurable. You see them once we start writing the code. One other thing that I'd like to mention in this theory lecture is hardware flow control. Okay, so I'm going to write hardware flow control. Basically, the hardware flow control is in place so that two systems that have very different processing speeds can still communicate. Okay, remember that I said it clocks based on the baud rate, but once information is received, some processing has to be done. Like in each of the system, there is a buffer. The buffer is the place that they hold the information that they receive. Okay, so system A is going to have its own receive buffers or buffer, and system B is also going to have its own receive buffer. Now, assuming that system A is faster than system B, then there could be a problem when it comes to communication. And that is where the hardware flow control comes in. So if you want to use hardware flow control, between the two peripherals, there is going to be what is known as RTS, that is request to send, and then there is also CTS, that is clear to send. And then this one is also going to have the same RTX, and then this one is going to have CTX. Okay, now you cross connect them as well. So the RTS of this is going to connect to the CTS of this, and then the CTS of this is also going to connect to the RTS of this. Now, how does this hardware flow control helps two systems that operate at different speeds to be able to communicate? Let's say system A is way faster than system B, and it is sending a bunch of information to system B. However, because system A is faster than system B, there would come a time, if we want the integrity of the communication to be guaranteed, there will come a time where system B will have to be able to signify to system A that, dude, hold on, let me finish processing what I have received into my buffer. And once I am done, I will let you know so that you can send further information. That is what the request to send and the clear to send pins are for. So the request to send is what it uses to signify to, so this one will use this to signify to system A. So it will be checking this line, right? System A will be checking this line. And there is a state that indicates that system B is ready to receive information or it is not ready to receive information. So when this one, system B, indicates the clear to send, then it is telling this system that I am ready to receive, and it's going to send information to it. So basically, the hardware flow control is just to help to alleviate a problem that can happen just because the two systems are not operating at the same speed. And I'm not talking about the baud rate, it's about the processing speed, right? If this one is sending things way too faster than this system here can process, then chances are that in the processing of the information that is being sent, maybe the problem could even come from the reception of the data. Like some data will not be received or will not be read properly, or even if they are read properly, they will not be interpreted properly. So this is when hardware flow control comes in, and all of these are configurable when you are writing your code. So this, I hope, helps, makes it clear, at least gives you enough theory about the UART communication protocol. In the next video, we will start writing code to send information between our microcontroller and our computer, but it's the same whether it's microcontroller to microcontroller, or microcontroller to sensor, or microcontroller to a PC. Thank you very much for watching, and I will see you in the next video.